Hello, hello. Good morning, students. Today we will see uh, ambient circuit law inside a magnetized object. This is the topic today. And in previous class, you have studied when an object is magnetized, uh, the field around that object is due to two parameters. One is due to surface current, secondly due to volume current, isn't it? The magnetic field around the magnetized object will be one due to surface current that exists on the surface, very outer surface, and secondly due to the bound current or volume current, we denoted with JB. So these things when come into ambient circuit law, usual ambient circuit law. In usual ambient circuit law, we discuss a line integral vector B dot dl equal to mu 0 times I, where the current is a free current. That current is due to the electron current, and that electron is free electrons. That free electron can move anywhere. But in a bound current, those electrons are not free. Okay, they are still bounded. They can move in some circular fashion. So we call it a bound current. So normal electron current, they can move from the entire bulk of the material. There is no problem. Anywhere it can move. But bound current, they can move in certain restricted regions only. Restricted regions, small specific region, beyond which they cannot go. Understand? So that is the property of bound currents. What will happen to such an object? How the ambient circular law is applicable for such a magnetized object? How these bound current will be accounted for? That is our point of discussion today. And initial ambient circular law, we have line integral V dot dl is equal to mu 0 times current enclosed. That's I enclosed. Okay, this is the current, and this is a line integral. So there is no confusion. Okay, current will be symbol free current, and corresponding the differential form was del cross B equal to mu 0 times J, where J is the current density, volume current density. Okay, volume current density, but not bound current density. Understand? So suppose now your material is not a simple copper wire. Instead, some other magnetic material, say iron. Suppose I consider a cylinder. Okay, a cylinder, a magnetized cylinder, and it is passing a current. So you have a current, normal electron current, free electron current, as well as material have some bound currents because it is magnetized. I hope the difference is clear. In our previous talks, we used a simple copper wire. We had only free electron current. But in this case, you have a magnetized object. So it consists of both free electron current as well as bound current. Okay, there may be surface bound current, there may be volume bound current, as denoted by the notations shown in the previous module. So how our equation will be modified? That is the question. Okay. So whenever a material is magnetized, we know there are two types of current. One is volume bound current, JB, denoted with del cross M, where M is the magnetization. We have discussed it. And secondly, you have the surface bound current, denoted by KB, and KB is given by M cross and cap, where M cap is the unit vector drawn at any point on the surface of that magnetized material. Okay. So these were our notations. Okay. So these are to be included in our present discussion when we are talking about ambient law in a magnetized object. Suppose this is our magnetized object. Okay. For example, a steel rod. A steel rod can be magnetized. So if you apply a voltage, there will be natural current also. Okay. Something like a copper wire, a magnetized steel will also pass current. So you have now free electron current as well as bound electron current. Two things are there compared to copper wire. Okay. So in addition to free electron current, there is a free current. In addition to bound current, there is a free current inside the material due to the free electrons present. So the total current now you can express as total current will be bound current JB plus free current JF. Free current means free electron current. Okay, so in Ampere's law, small modification comes because you have free electron current due to free electrons and bound electron current due to the magnetization. Understand? They are bounded. They form small micro circular circulating currents. Micro circulating currents. So what happens? Your Ampere's law you have to modify. You have curl B is equal to mu 0 J. Now your J consists of bound J and free J. Okay, so we modified our equation like this: mu 0 times JB plus JF. Okay, so again you have your bound current. You had an equation. Bound current JB was curl M. So we replaced JB with curl M. Okay. So what happens? You bring your curl M to the left hand side and bring your mu 0 also to the left hand side. So now you will get this kind of an equation. Curl B upon mu 0 minus curl M is equal to JF. JF is the free current. Okay. Now you can see curl here and curl here. You take the curl outside. So if you take the curl outside, you can write this equation as curl del cross B by mu 0 minus M is equal to J. Okay. So you have a bracketed term. It's a bracketed term. You can replace this bracketed term with a notation called H. H. This H is have a number of names. Some people call it a magnetizing field. Some people call it a magnetic field induction. So many names are there. Okay, so now we call it simply H now. So we once we replace this bracket term with H, you get del cross H equal to JF. Understand? Initially we had del cross B is equal to mu 0 J. Now that J got defined, modified, because we have a magnetized subject, there may be bound current. So in order to account that bound current, we replaced our J with JF. So del cross H is equal to JF is the new Ampere's law. Understand? New Ampere's law in magnetized objects. So H has different names in different books. One name is magnetic field intensity, magnetizing field. Some books called magnetic induction. So anyway, H is something which occur when the material is getting magnetized. Okay, H. And you can have a corresponding integral form because this is a differential form. Understand? So what you have to do, you integrate both sides with the surface integral, taking surface integral on both sides because they are functions. Okay, function can be integrated, vector function, both are vector functions. So you integrate with the surface integral del cross H dA and JF dot B. So when you take that, you can see the left hand side you can apply what is called a Stokes theorem. Okay, this surface integral you can convert into line integral. How you will convert line integral? Like this. Okay, del cross H dA will give you line integral, closed line integral S dot dA. Okay, the closed line. So I think the left hand side you can replace with a closed line integral S dot dl. So we get a closed line integral S dot is equal to surface integral JF into dA. JF into dA. Okay, so this is surface integral JF into dA. And current density into area will give you the current actually I. So JF into dF give you IF. Okay, IF integral of Jf dA will be If. So this is the ambient circuital law in integral form. Line integral, you please put a closed line integral. It's a closed line integral. You take a closed loop like this, okay, like this. So this is a closed line integral. S dot dl is equal to If. So this is the modified Ampere's law by taking into account volume current, bound current. Understand? So this is a more suitable form. Closed line integral H dot dl equal to free current, or more clearly, free enclosed current. Free enclosed current. For IF enclosed is the total free electron current passing through the material. Okay. For visualization, you can take this figure. What is the closed line integral? This is the closed line. So the total current now passing through this is taken IF1, because bound current is accounted here. Okay, you don't think that your bound current has gone or forgotten. No, it is included inside the vector H. That is all. You see the previous steps, you will understand that your curl M is included here. Curl M is included. That is the reason. Okay, so I hope the idea is clear now. So the free current inside a material, you can measure it, because using equipments, galvanometer or ammeter, you can measure free current. So obviously you can find what is called H. So H is a measurable quantity. Okay, H is a measurable quantity. So here is a small problem. For an arbitrarily magnetized object, who that del dot H, divergence of H is equal to minus divergence of vector. Okay, very simple problem. So let us try to do it. Already we know del dot H, divergence of H is given by, you replace your H. H is equal to B by mu 0 minus H. That we know very well. Okay, so B by mu 0 minus H. So you can apply del dot on D by mu 0, del dot on M. So what we will get? We will get 1 by mu 0, this is a constant, into del dot B minus del dot M. Okay, and what is del dot B? You know, divergence of B is 0. Divergence of B is 0. So that can be removed. So then what is left? The first term is disappeared. So then we have del dot H is equal to minus del dot. Suppose the magnetization is uniform. Del dot M exists when M is diverging or M is non-uniform. Okay, if M is a constant one, uniformly magnetized, then del dot M will be 0. Understand? Okay, in that case del dot H will be 0. Okay, so if it is not uniform, non-uniformly magnetized, then there will be a del dot H. Of course, there will be a del dot H. Okay, if it is uniformly magnetized, then del dot H will be equal to 0. So that difference must be understood. Don't assume that always del dot B and del dot H are 0. No. Okay, del dot H and del dot B are not always 0. That depends on whether the material is magnetized or not. That is very important. We want to introduce another simple concept. It is called magnetic susceptibility and magnetic permeability. It's a very simple topic. This is a material constant. This it varies from material to material. Different materials have different magnetic susceptibility, denoted with chi m. Okay, chi m. So usually this is very useful for many material like paramagnetic material and diamagnetic, because inside such materials magnetism exists until the applied field is maintained. Once the applied field is withdrawn, their magnetic field is disappeared. Okay, magnetic field is disappeared. So you have two parameters. One is the magnetizing field, or you can say the applied one. One is magnetization. So one is the cause and other is effect. H is the cause and M is the effect. So M is proportional to H, you can say. Understand? M is proportional to H, or M is equal to some constant in H. That constant is called magnetic susceptibility. Okay, this chi E, magnetic chi, usually we can call it chi M. Chi M, that's more good. Chi M is magnetic susceptibility, and you already know that chi M is equal to chi E into M. I wrongly put it as E. You take it as chi M. Okay, chi small m, magnetic, because this kind of a thing will come in even in electrostatics, where this is chi E. That is electric susceptibility. Here it is chi M, is wrongly shown as chi E. You put it as chi M. Okay, so now you have the H here, and in this equation you can rearrange this equation. You get a B is equal to mu 0 H plus mu 0 M, and of course the M you can replace. M is equal to chi M into H. So we have B is equal to mu 0 H plus mu 0 chi M H. Okay, and there is an H on both sides, and there is a mu 0 in both terms. To take it outside, so you can write B is equal to mu 0 1 plus chi E into H. Okay, H is a common thing taken outside. Similarly mu 0 also. And this 1 plus chi E, we call it as relative permeability or relative magnetic permeability. Understand? You notice a new term mu r. Okay, so where this mu r is equal to 1 plus chi E. Okay, and mu 0 and mu r, when you multiply, what we get is called absolute permeability. Absolute permeability, that is denoted with mu. Mu is called absolute permeability of the medium. So you get a relation, a beautiful relation, that magnetic flux density B equals absolute magnetic permeability multiplied by H. B equals mu times H. Understand? So here mu is called absolute magnetic permeability of the medium. That is given by mu equal to mu 0 mu r, or you can write as a ratio also. Mu r is equal to mu by mu 0. You have already a relation like this in electrostatics, where you use epsilon r equals to epsilon divided by epsilon naught. So this is a similar relation for magnetic material. The other one is for electric material or dielectric material. So that is the difference. Okay, so it's a very simple topics, and here is a question now. A paramagnetic material has a magnetic field intensity of 10 raised to 4 ampere per meter. So this is in fact H value, H, capital H. If the susceptibility of the material at room temperature is 3.7 into 10 raised to minus 5. Susceptibility means chi M, okay, magnetic susceptibility. Calculate the magnetization M and the magnetic flux density B inside the material. A very simple problem. You see, H is given and chi is given. So, okay. So what we can do? We can find magnetization M. Very simple procedure. Once you get the magnetization, you can do what? You can get B. That is the second question. Magnetic flux density in the material. That is given with a standard equation. Already we have derived it. E equals mu 0 times M plus H. And now we have in hand M as well as H. H is already given. So B can also be computed. Magnetic flux density can be also be computed. So even though I did this problem here, you can copy it down in your assignment in your notebook. It's a very useful problem, most likely to be asked in the examination. Okay. And now we have an assignment problem also here. So very simple question. A magnetic material has a magnetization of 2300 ampere per meter. Okay, magnetization, you know, magnetic moment per unit volume, and it produces a magnetic flux density of 0.00314 Weber per meter square. Okay, this is B. Calculate the magnetizing field H and the relative permeability of the material. So with the previous ideas already we discussed, all those ideas will be useful. Those ideas will be helpful to do this problem. The likely answers are shown here. You can use it as a hint. So complete this assignment and submit in due time. Okay, hope the ideas are clear. You please try to watch the video at least twice to get the all ideas clear. So with these remarks, let us stop this session. Thank you all. Thank you.